Welcome to the fourth and final part of Unit 13. In this part, we're going to be focusing on multidimensional collisions. With a multidimensional collision, you must conserve momentum in all directions, and if it is elastic, you must also conserve energy. This is the link to the same PhET simulation that we looked at in the one-dimensional collisions. There is actually a feature on it that lets you look at multidimensional collisions, and we will look at that shortly. In this part, we're going to analyze the same collision twice, once for when it is elastic and once when it is completely inelastic. To begin with the elastic collision, here is the setup of the problem. You have two masses. I give you what their masses are and what the initial x and y velocities are for each of the masses. Now, as I said, you must conserve momentum in both directions and you must conserve energy. Now, in the elastic collisions section, we derived an equation that must be true for elastic collisions. It's equation 26 on your equation sheet. That must hold for multidimensional collisions as well. So for both dimensions, we're going to end up with two equations. Okay. I'm going to start by thinking about the x direction. And I'm going to begin with looking at the equation that has to be true for an elastic collision. So V1 x initial minus V2 x initial has to equal V1 x final, that should be a 2 if I use the equation correct, minus V1 x final. V1 x initial minus V2 x initial is 1 meter per second minus a negative 0.5 meters per second. So that's V2 x final minus V1 x final. Or in other words, V2 x final equals 2 meters per second plus V1 x final. We're now going to move over to the momentum equation. And eventually we'll need to use the one that we just derived in this equation as well. So P initial x has to equal P final x. So M1 V1 x initial plus M2 V2 x initial has to equal M1 V1 x final plus M2 V2 x final. Plugging in numbers, this is 0.5 kilograms times 1 meter per second plus 1.5 kilograms times negative 0.5 meters per second equals 0.5 kilograms V1 x final plus 1.5 kilograms V2 x final. On the left-hand side of the equation, I can multiply and add this all together, and I get negative 0.25 kilogram meters per second. On the right-hand side of the equation, I can plug in the equation I have for V2 x final that I got from the energy equation. That was 1.5 meters per second plus V1 x final. Okay. So I'm now going to distribute through the parentheses and collect like terms all at once. I have two terms that involve V1 x final. It's this one and this one. So 0.5 kilograms V1 x final plus 1.5 kilograms V1 x final results in 2 kilograms times V1 x final. I have two terms that don't involve V1 x final, the negative 0.25 kilogram meters per second on the left hand side and the 1.5 kilograms times 1.5 meters per second on the right-hand side. When I combine those, I get negative 2.5 kilogram meters per second, which gives me that V1x final equals negative 1.25 meters per second. I can now find V2x final because it equals 1.5 meters per second plus V1x final from, again, the previous equation we got looking at the energy equation. 1.5 minus 1.25 is 0.25 meters per second. And we are done with the x direction. We're now going to move on to the y direction and do the exact same analysis. So we're going to get V1y initial minus V2y initial equals V1y, nope, that should be a 2 again, V2y final minus V1y final. Okay, so V1y initial minus V2y initial, plugging in numbers from the first slide, is 0.3 meters per second minus a negative 0.5 meters per second. Combining those two gives me 0.8 meters per second equals V2y final minus V1y final, or in other words, V2y final equals 0.8 meters per second plus V1y final. We can now look at the momentum equation. So the initial momentum in y has to equal the final momentum in y. So that's m1 v initial y, v1 initial y, plus m2 v2 initial y has to equal m1 v1, I guess I should do it the same order I did above, y final, plus m2 v2 y final. Plugging in numbers here, 0.5 kilograms times v1 y initial is 0.3 meters per second. M2 is 1.5 kilograms times V2 y initial, which is negative 0.5 meters per second. That equals 0.5 kilograms times V1 y final plus 1.5 kilograms times V2 y final. Okay, I'm going to combine the right-hand side. When you multiply and add, you should get negative 0.6 kilogram meters per second. And that'll equal 0.5 kilograms V1y final plus 1.5 kilograms. And now I'm going to plug in our answer from above, 0.8 meters per second plus V1y final. As I did before, I'm going to combine like terms. So I have this term and this term, both of which involve V1y final. And that results in 2 kilograms V1y final. I have two terms that do not involve the V1y final. And when I multiply 1.5 times 0.8 and move it to the other side, that gives me negative 1.8 kilogram meters per second, or in other words, V1y final is negative 0.9 meters per second. I can take this and plug it in up here and get negative 0.1 meters per second. And now we have our solution. Now, we can go and plug this back in and verify that energy and momentum are conserved. Rather than me taking the time to write that all out, what I did instead is I've made an Excel spreadsheet that does this for us. Before we get to that, I said, hey, let's look at the simulation. So here is the simulation. If you look, mass 1 is 0.5, initial velocity of 1 and 0.3 meters per second in x and y, and mass 2 is 1.5 kilograms with initial velocities of negative 0.5 in both directions. Right now the elasticity is set to 100%, and when I hit play, they come together and collide. And it does, on the surface, the correct things. But if you look, the answers for the final velocities do not agree with what we found. Okay? I don't know quite why not, but I did make sure, as I said, that our numbers work. So here is, coming in, hold on. I'm having some technical issues. Here is the Excel spreadsheet. So you can see the numbers at the top are from the simulation. So I have M1 with all of its initial velocities and final velocities and momentums and energies, and M2 down below it. Okay, so first thing is initial momentum in X is negative 0.25, and initial momentum in Y is negative 0.6. So I'm looking at these two numbers here. When I look at what comes from the simulation, I get something that is close to, but not exactly the same numbers for the final momentum. And the energies are similarly just not quite right. Okay, but everything is very close. It's very close. When I look at what we did in the PowerPoint and the math, so you can see here's the V1Y final of negative 0.9 and V2Y final of negative 0.1. And similarly for V1X and V2X final. My momentums, initial and final, are exactly the same, and my energies are exactly the same. So I conclude from this that our math is spot on. We've conserved both momentum and energy with what we've done. There's something going on with how the simulation is doing the calculations that results in it giving things that are close but not quite right, and I don't know what that is. I'm actually going to ping the people at FET and say, hey, something's up. See what they say. Okay, we will look at that again in a minute. We will look at this again in a minute. In the meantime, let's do the same collision again, but in this case, we're going to deal with a perfectly inelastic collision. And remember, when you have a perfectly inelastic collision, the two objects stick together and move off together. So V1 final is going to equal V2 final, which is going to equal V final in this case. Okay, we can expand this out to say V1 final X will have to equal V2 final X, which I'm going to write as V final X. Oop. Yeah, we can leave those arrows, as it'll work. And V1 final Y has to equal V2 final Y, which has to equal V final Y. Okay, and remember, this is a result of it being perfectly inelastic. They stick together. Okay, so let's begin by looking at X again. So P initial X has to equal P final X. So m1 v1 initial x plus m2 v2 initial x has to equal m1 v1 initial, final x plus m2 v2 final x. Okay, now plugging in everything we know. We know that this is 0.5 kilograms times 1 meter per second plus 1.5 kilograms times negative 0.5 meters per second. And that has to equal m1 plus m2 v final x. Because they have the same final velocity, I can factor it out. So negative 0.25 kilograms meters per second equals 0.5 kilograms plus 1.5 kilograms v final x. And I find that v final x equals negative 0.125 meters per second. I'm sure you're thinking at this point, this is much easier. Okay, doing the same thing in the y direction. I have m1 v1 initial y plus m2 v2 initial y has to equal m1 v1 final y plus m2 v2 final y. Plugging in numbers again, 0.5 kilograms times 0.3 meters per second plus 1.5 kilograms times negative 0.5 meters per second has to equal, again, factoring it out, m1 plus m2 v final y. Multiplying this all together gives negative 0.6 kilogram meters per second. That equals 0.5 kilograms plus 1.5 kilograms v final y. And when you add and then divide, you get v final y equals negative 0.3 kilogram meters per second. Okay, so as before, we're going to go look at the simulation. Here it is. Notice in this case, I've set elasticity to 0. Initial velocities all look like what we had originally. So I'm going to let it go. Okay, first thing to notice, they don't stick together. So something's a little goofy there. Let's try it one more time. I'm going to stop it sooner. Okay, so here we are. Okay, and now I'm going to bring in theory, the same Excel spreadsheet, but I have a tab for inelastic collision as well. So let's see if we can set this up so we can see both sets of numbers simultaneously and make sure I plugged everything in correctly. Okay, so V1 X final negative 0.14, V2 X final negative 0.109, and in the Y direction that agrees as well. So if we make this bigger again and look at the simulation, again, the final momentums are off just a little bit. In fact, if you look, they're the same amount off, at least in the Y direction, that they were for the elastic collision. They're close, they're just not quite there. And we wouldn't expect this one to conserve energy, and it really, really doesn't. So there you go. If we look at what we did in the math, we found V1 X final of negative 0.125 and y final of negative 0.3, and I've plugged those in the same in both places. And my initial and final momentums in x and y match perfectly. And again, energy is not conserved. So on the surface, the simulation is doing something that is more or less correct. It's certainly giving the correct gist of the output, but it's not calculating quite right, and I'm not sure where the problem is in the background of the code. This concludes the multidimensional collision section of Unit 13.